All right, so Avogadro's principle is actually kind of a supporting idea for the gas stoichiometry that we are about to be doing. Mr. Avogadro is the guy that we have to blame for all of that mole stuff that we have to do in chemistry, but it is such an important idea in chemistry that there's a little bit of it everywhere. Mr. Avogadro actually came up with his number by studying gases, because those were the particles that were the easiest to be counting and quantifying, as they were all separate. And so what he came up with, which was a rule for how gases can behave as well as part of his studies of them coming up with that number, is that if we have equal volumes of gases, even if, like we're about to see, I'm dealing with completely different gases like oxygen, O2, and ammonia, NH3, as long as I have equal volumes of those gases and they're at the same temperature and pressure, then there are going to be an equal number of molecules in those gases. I'm going to say equal amount of molecules. And because he was the mole guy, and he was the person that came up with the idea of using this thing called a mole to count our number of molecules, it's not just an equal amount of molecules, it's also an equal number of moles of those molecules will exist even for completely different gases. As long as our volume, temperature, and pressure are the same, our moles will be the same. So these problems really just try and hit home that idea. And in this first example, it tells us, like we already saw, we have two completely different gases, oxygen and ammonia, but I have the same volume containers, and they are evidently at the same temperature and pressure. So we have met all of the conditions that Mr. Avogadro's principle was set up for. So if I know that there were exactly 2 times 10 to the 23rd molecules of oxygen in its container, then I would also be able to determine that there are exactly 2.00 times 10 to the 23rd molecules of ammonia in the same size container at the same temperature and pressure. If everything else is the same, the number of molecules will be the same, even if they're different gases. Now, that's very useful and all, but we hardly ever have everything exactly perfectly the same. But as long as we stay at the same temperature and pressure, even if our gas volumes are different, they're going to remain proportional. So here we still are dealing with oxygen and ammonia, and I know exactly how many oxygen molecules I have. But now I have my ammonia in a container that's twice as big. It's 10 liters instead of the 5-liter container of oxygen. But as long as they're at the same temperature and pressure, if my volume has doubled, then that's like having 2 5-liter containers of ammonia. I'm going to have twice as many total molecules if I had 2 of those containers than I did at 1. And each of those 5-liter containers of ammonia would have exactly the same number of molecules as my oxygen. So I'm going to have 2 containers. Well, it's 1 container. You can just kind of imagine that that 10-liter container is 2 5-liters together. It's twice as big. It's going to hold twice as many molecules, which means that's going to be 4 times 10 to the 23rd molecules of ammonia in that container. And like we said up above, we can do this with specific numbers of molecules, but we rarely care exactly how many molecules we have. We have the unit of moles for a reason, because that's our standard unit to count the amount of molecules that we have. So if we still have these containers, 5 liters of oxygen, 10 liters of ammonia, I would still expect twice as many molecules in my 10-liter container. But if I only know the number of moles of molecules here, my 5-liter container has 2 moles, then what I know is that my 10-liter container will be twice as big. So what I know is that there will be 4 moles of molecules in that ammonia container. And it throws people off sometimes that it asked for molecules and my units on my answer here are moles. They are not the same thing. But this is kind of like if you asked me, if I was bringing donuts to class or something, and you asked me, how many donuts are you bringing, Mrs. Gunter? I could either tell you I'm bringing 36 donuts, or I could tell you I'm bringing 3 dozen donuts. Both of those answers answer your question. They're telling you exactly how many donuts we're bringing, and they are equivalent. It's just when I say 36 donuts, I'm telling you my answer in donuts. But I can also use the counting word dozen to count how many donuts I have. It's just easier to group them sometimes, and 3 dozen is how many I'm bringing. So here I asked you how many molecules. Well, it's going to be 4 moles of molecules. So that's Mr. Avogadro's simplest idea with our gases, is that our gases, molecules, and moles are proportional to their volume. Now, he took it a step farther, and because he was all about standardizing things, and by standardizing, I mean setting everything equal to this mole idea that he came up with, like our molar mass was 1 mole of a substance is equal to a certain number of grams. Avogadro's number was 1 mole was equal to a certain number of molecules or atoms. Well, he wanted to standardize our molar volume of any gas. And so what he did is actually kind of deceptively simple. It is simple. It's just one equation. What he did is he took the ideal gas law and he just solved for volume, which we all could do. It'd be nRT over P. And the only thing that he did that was special here was he standardized everything that he plugged in here. So because this is a rule at standard temperature and pressure, he plugged in our standard temperature, which was 273 K, and then he used one of our standard pressures, and it could have been any of them. It doesn't really matter as long as the R value matches. So here, if I use my 1 ATM as my standard, and my R would have to be 0.8 or 0.0821. And then he said, okay, I want to set this volume equal to 1 mole. So he plugged 1 in for N. It's a really simple calculation here. And you can do it too. If you do this multiplication and division, what you get would round to 22.4. So that's all that he did here. And what that does for us is that as long as we are at STP, and let me go ahead and clean this up a little bit, then 1 mole of any gas will always equal 22.4 liters. Now, this isn't technically something you have to memorize. It is on your equation sheet, although it looks a little bit different. It's written as 22.4 liters per mole, and it says that that is the standard volume of a gas at STP. So it does remind you that that is only going to be true at STP. But kind of like when we had molar mass, I had some number, and the actual number, if it wasn't used as an equation or a conversion, was grams per mole. It's technically grams over moles. And we pulled that apart to make the 1 mole part be on the other side of the equation. The same thing is going to happen here. If we want to turn this into its equation form to help us use it in dimensional analysis, we have to remember to pull the mole part over. Everything that has to do with moles is some crazy number set equal to 1 mole. And this isn't that crazy of a number, not as bad as Avogadro's number, but still, if we want to be able to look at our equation in this form to help us do our dimensional analysis and stoichiometry work, we're going to have to remember when we see this on the equation sheet to use it, to move it really over so that we have 22.4 liters equals 1 mole. That's our goal. That's going to make it just like all the rest of the dimensional analysis we've always done. So let's just finish out these couple of problems down here at the bottom, and they're pretty quick because we can do this all in dimensional analysis. You might even recognize problems like this from our quiz or a practice quiz, and we could solve these just like Mr. Avogadro did by plugging in our standard temperature and standard pressure with this volume into that ideal gas law. But we can do that much quicker with a lot less rounding and possibilities for errors if we use dimensional analysis. Remember that if I have liters as my given, and that's the only number given to me here, then liters on top means that I'm going to want to put liters on the bottom of the next bracket, which means I'm going to be taking this 22.4 liters, putting it on bottom. That means the 1 mole side of my equation is going to fill in the top. And that's all I need to answer the question. All it wants to know is how many moles are in that volume at our standard temperature and pressure. And then when I do that division, we get 6.0267 and more numbers there. But this is dimensional analysis, so we're going to look at our given, which was 3 sig figs, round our answer to match that. So 3 sig figs here means my 6 will round my 2 up to a 3. So 6.03 is my final answer. And of course, it was asking for moles, so the units on my answer better be moles. Now, like I said, that last problem could definitely have been worked with the ideal gas law, and it's actually not that much more complicated to do it that way. But question number 2 is really where this conversion really helps us a lot, because if we did use the ideal gas law here, the ideal gas law can't solve for grams. Grams is always a sign that I'm going to have to do a little bit of dimensional analysis to get from moles to grams, which means I'd have to do the ideal gas law, solve for moles, meaning look and solve for N, do PV over RT, get a number out, and then I'd be doing dimensional analysis anyway. So if I notice that it's asking me for grams and I'm at STP, then I can get from my volume to my moles, just like we did up here, and then I'm just going to need to go one step farther to get those moles into grams. So let's do it. Slightly different given. Make sure that that is just 35 liters, not 135 in this problem. And the problem starts off the same way. Because I was given liters, I have to have that liters on the bottom. It's just that I'm not done now because I don't want moles, I want grams. So I'm going to have to go one step farther using the molar mass of nitrogen, which hopefully you remember is a diatomic. It is N2. So I need to add up 2 nitrogens, and 28.014 is that number, and that's grams per mole, but the 28.014 grams is the part that goes on top. The per mole, the 1 mole part, goes on the bottom, just like these parts were separate here. And now I'm done. Setting it up, just have to put it in my calculator. And 43.771 is what I got out of my calculator. Checking back at my given, I just had 2 sig figs. So I just want to keep these first 2 sig figs, but the third one, that's 7, is going to round my 3 up to a 4. So my final answer here is 44 grams. Now, question 3 doesn't have any surprises in it. It's just like question 1 or 2, so make sure you read it carefully. It's going to be set up and worked out very much like one of those. So set that up, work that out. I'm going to scroll down to help you out with number 4, which is a little bit different. And the way that this is different is because it gives me grams. So automatically your first instincts should be that we have to turn these grams of ammonia into moles. And just like what we were doing back in unit, what was that, 8, and in unit 6, grams to moles, I just need to add up the molar mass of this NH3 thing, which ends up being 17.031 grams per mole. And that means that that gram number goes on bottom, 1 mole goes on top. But I didn't want to stop at moles. I want to know the volume of this at STP, which is where that 22.4 number comes back in, because that can get me from these moles to my liters in one step. And I know that in our equations before, we really liked it when it told us that something was a volume or a pressure. But here, we do need to keep in mind that we're not solving for V. V isn't the units we're looking for here. We're going to be measuring our volume in liters. So that is going to help you remember that we need the liters equation here. So 1 mole has to go on the bottom this time because I had moles on top. All the other problems that we've worked so far had the liters part of that on the bottom. But remember, they can go either direction, just like my molar mass. And every other conversion can go either direction. It's the diagonal rule. Looking at the units at the top of the previous bracket is always going to tell you what should be diagonally down on that next bracket. So this is all set up. Let me clean up my arrows here. And hopefully if you're plugging this into your calculator, that your calculator is telling you the exact same numbers that mine is. If it's not, let me know and I'll help you get there. But I just want you to round this final answer, put your final units on it, and then make sure that you finish up this problem as well. This answer should turn out to be less than 1, so kind of between 0 and 1. If you're getting a decimal answer, that is perfect. Just make sure that it has the right number of sig figs, and you're good to go. That's all the notes we got for today in class, and this is going to be really helpful to know ahead of time for when we're doing our gas stoichiometry work next class. So have a good rest of your day.